Welcome back to Industrial Automation course, Lecture 3, PLC Hardware Components. Today's topic will be as follows. List and describe the functions of the hardware components. Describe the basic circuitry and application for discrete and analog I/O modules. Explain I/O addressing. Describe the general classes and types of PLC memory devices. Describe different specifications of I/O modules. Define the central processing unit, CPU, and describe its role. Specify different PLC programming devices. And finally, define the concept of human-machine interface, HMI. The I/O section. The input-output I/O section of a PLC is the section to which all field devices are connected and provides the interface between them and the CPU. Okay, so here we have input-output arrangement are built into a fixed PLC. Okay, so this is a fixed PLC, and the input and outputs are integrated with the CPU and power supply unit. Here we have a modular PLC. Modular types use external I/O modules that plug into the PLC. Rack-based I/O section made of an individual I/O module. So here we have our modular PLC, and we have multiple racks. On each rack, we could insert one input or output module. Input interface modules accept signal from the machine or process devices and convert them into signal that can be used by the controller. Okay, so it accepts signal from devices and convert it to a proper signal for PLC. Output interface modules convert controller signals into external signals used to control the machine or process. The hardware assembly that houses I/O modules, process modules, and the power supplies is referred to as the chassis. So here is basically the chassis, and we have CPU and we have I/O racks. A logical rack is an addressable unit consisting of 128 input points and 128 output points. Okay, so here basically we have 8 slot chassis. We have 0 to 7 slot for the input and output, and it consists of 128 output rack. It means that we could cover 128 input or output. The ability to locate the I/O modules near the field devices minimizes the amount of wiring required. The remote rack is linked to the local rack through a pair of communication modules. So here we have our local I/O, and here we have a remote I/O. So local I/O are those ones are located on a rack of the main rack of PLC. We have a processor or CPU and power supply unit. So this is basically the main block of our PLC, and here we have remote I/O. So it minimizes the amount of wiring. This is the main reason of using these remote I/Os for some applications where the outputs and inputs are far from the PLC. We use these remote I/O blocks to collect all these input output, and let's say with one Ethernet cable we could transfer the data to the main block of PLC. PLC's memory system stores information about the status of all the input and outputs. To keep track of all this information, it uses a system called addressing. Okay, so we have a memory, and each of those inputs outputs have an address. An address is a label or number that indicates where a certain piece of information is located in a PLC's memory. Rack slot based addressing schemes are used with Allen-Bradley PLC5 and SLC500 controllers, and tag-based addressing is used with the Allen-Bradley control logics controllers. Okay, so these are two different type of addressing methods. Similar method are common and are in practice in different type of PLCs, and we don't have to specifically use Allen-Bradley control logics. These are just examples here to show us what type of addressing we have, and basically each input and outputs have an address in a memory. Okay, so here we have that the PLC5 rack slot based addressing format. Here we have one example, I1 2713. So I is an indicator of input. It's located in file 1, rack 2, group 7, and bit 13. So here we have for example, here we have file type, output or input. We have a file number, for this case is 1. We have here 5 delimiter, which is this, rack number, group number, and finally the terminal number. Yes, and these are different other examples here. So the advantage of this type of addressing is that it has a connection with the physical devices, and is very easy to understand where that basically input is located. It's located on rack 2 file 1 and its input bit 13. So we could physically basically find the location of that input and output on or input-output module cards. This one here we have SLC500 rack slot based addressing format. This is another type of rack slot based addressing. Here we have output slot 4 and terminal 15. So it's a simplified version of the other one, and you could see the definition of each alphabet or number here, and other examples you could find as follow. Every input and output device connected to a discrete I/O module is addressed to a specific bit in the PLC memory. Okay, this one is very important. Look, here we have this input module, and here we have the output module, and here we have our PLC. We have two inputs, one limit switch and one push button. Both of them are indicated by I because they are input. One of them is 10 and the other one is 11. This is the bit address of these inputs. And here in the memory of the PLC, we could refer to those inputs by selecting the address here. For example, the input one is the first input is I10. The value of this input for this moment is 1. It means that it's true or is close here. And the second one, the value of the second one is 0. It means that it's open or is false at this moment. And the output here is, let's say, 030, and the value at this moment is 0 or false or off. At this moment, here is the PLC ladder logic program. As you could see, we have 2 inputs in series and finally or coil or output. So since the logic doesn't hold here, and this one is false, and this one is false, and this one is true, so then the output is false, or the coil value is 0 and the output is off. Analog I/O modules use a word addressing format. The bit part of the address is usually not used, but can be addressed by the programmer if necessary. Okay, so here you see that we have 2 analog input and analog output, and both of them are connected same as digital inputs and digital outputs to analog modules of modular PLC. Allen-Bradley control logic controllers use a tag-based addressing format. Okay, so control logic is basically the program are used to program Allen-Bradley PLCs. Instead of a fixed numeric format, a tag alphanumeric name is used to address data. And the field devices are assigned tag names when the PLC ladder logic program is developed. So here we have the tag and the description assigned to alias tag. Alias tag pointing to base address, and the base address and input instruction. So this one is instruction, this one is the base address, and we have the alias tag, yes? So we could basically assign a name, for example, start to I1.0. And instead of using that, the direct address of I1.0, we could use the alias name or tag. PC-based control runs on personal or industrial hardened computers, also known as soft PLCs. They simulate the functions of a PLC on a PC. Yeah, so we could basically simulate a PLC or PC by having some specific input-output cards, like this one. The implementation uses an input-output card in conjunction with the PLC as an interface for the field devices. So it simulates our PLC, but of course we cannot use these type of PCs and input-outputs in industrial environment because of less durability and less reliability of this type of PCs. Combination I/O modules can have both input and output connections in the same physical module. So those PCs could have these type of I/O modules, input outputs. Both of them are in the same physical module, and they accept digital or analog IOs. An IO module is made up of a printed circuit board and the terminal assembly. Okay, so this one is the printed circuit board and this one is the terminal assembly. The printed circuit board contains electronic circuitry. The terminal assembly is used for making field wiring connections. Yeah, so we could have a connection of field or field devices here, and here we have our main circuit, electronic circuit. Most PLC modules have plug-in wiring terminal strips that plug into the actual module. Okay, so here is a plug-in. If there is a problem with the module, the entire strip is removed and a new module is inserted and the terminal block is plugged into the new module. Okay, so we could just replace the module. IO module can be 8, 16, 32, or 64 point cards. Yes, so the point card point or number of inputs could have 8, 16, 32, and 64 inputs. The points refers to the number of inputs, outputs available. A high density 64 point card provides a greater space saving, but with less rated current output per output. So we should have appropriate number of points for our specific application. If the number of inputs are 8, we should avoid having a card with number of 32 or 64 for the cost aspect. Plus, as you could see here, for the rated current and the space. Discrete I/O modules. When we say discrete, we mean digital I/O. The discrete I/O interface module connects field input devices of the on and off nature, 0, 1, digital. The classification of discrete I/O covers bit-oriented inputs and outputs. Okay, so here we have some sort of inputs and outputs. Each discrete I/O module is powered by some field supply voltage source. Since these voltages can be of different magnitude or type, I/O modules are available at various AC and DC voltage rating. So we could have one, let's say, input module of AC type and 48 voltage, the other one 120 voltage, the other one, let's say, DC 120 volt. Yes, so based on our sensors, based on our field devices and what they need as a power and current grade, we could use different type of I/O modules. The modules themselves receive their voltage and current for proper operation from the back plane of the rack enclosure into which they are inserted. Back plane power is provided by the PLC module power supply and is used to power the electronics that reside on the I/O module circuit board. So here is our power supply and here is the back plane power, and you see that when we insert one module, then it will be connected to the power supply, and based on the type of the module, it will draw a specific current and accept different type of voltages. A discrete input module block diagram. Here you could see the block diagram. The circuit is made up of a power section and a logic section. So here is the power section, and here we have our logic section. Okay, so here is our input module. You're explaining what are the different sections, electronic sections of the module. An optical isolator is used to provide electrical isolation between the power and logic circuit. So we have this optical isolation here, or optoelectrical isolation here between the power and the logic that connects basically these two parts. And this part is very specific to industrial PLCs to increase reliability of the data. The input LED turns on or off, indicating the status of the input device. Okay, so this is input status indicator. It's just the LED on front panel, and the operator could see the status of that point or the terminal. But let's see what's happening here. We have our input or switch, and we have 120 volt AC in this specific case. When the switch is turned on, then we have current in the circuit, and this inside this optical isolator, we will have a light source, emitter, and have a light source receiver. So this optoelectrical isolator first isolate the circuit from ambient lights and from any electrical noises in the circuit or in the environment. So by this method, we could have very reliable transformation of the data from the power section with high voltage AC to low voltage DC logic circuit. And here now we could send a signal to the PLC for further processing, and we could use that inside our logical program, ladder logic program, or any other type of PLC programs. Okay, let's see the input module in more detail. We have here a AC discrete input module schematic diagram. When the push button is closed, AC is applied to the bridge rectifier input. Okay, so this is the rectifier that drops the voltage to DC or low voltage. This results in a low-level DC output voltage that is applied across the LED of the optical isolator. So the LED here inside that optical isolator will be on and is emitting light. When the light from the LED strikes the phototransistor, it switches into conduction. Yes, so now this switch is turned on, or the switch is closed, and we will have a valid logic in the digital logic circuit. And the LED will be on here that shows the status of the input. So almost the same block diagram we have on the output module. We have, it's just a reverse, yes, kind of is reverse. We have the logic section first and the power section comes after. The module is composed of the power section and the logic section, coupled by an isolation circuit. The power output interface can be thought of as an electronic switch that turns the output load device on and off. Okay, so once the program inside the PLC turns or output on, and the coil, let's say in the program, will be true, then here the logic circuit will send a signal to the power circuit. So here we have low voltage, here we have high voltage. So the load here, it's on 120 volt AC. And this one acts as a relay and will turn on the load. So here we have that output module in more detail. We have AC discrete output module schematic diagram, very similar to the input module. When the processor calls for the output load to be energized, a voltage is applied across the LED of the opto isolator. So here, basically this LED here is on. This in turn triggers the triac AC semiconductor switch into conduction, allowing current to flow to the output load. So, okay, so this is a basically triac AC semiconductor. It's a type of switch and will be triggered by the light of the LED, and which acts as a relay, yes, which acts as a relay. And now we have a closed circuit at the output, and the output will be. Individual AC outputs are usually limited by the size of the triac to 1 ampere or 2 ampere. Okay, so that triac has some limitation, and we should have a matching between our output current and the triac current. For controlling larger loads, an interposing relay is connected to the output module. The contacts of the relay can then be used to control a larger load or motor starter. So here we have that interposing relay coil to protect the output module and PLC from overload, from basically drawing high current or shocks from the load, yes? So for example, on cars, the starter draw a huge amount of current at the beginning, and they use these interposing relays. So triacs have some limitations, and we should use relays for larger loads. Discrete output modules are used to turn field output devices either on or off. Output modules can be purchased with transistor, triac, or relay. So triac and transistor also act similar to relay. And point of using all of these type of devices is to separate our logic circuit from the power circuit. On the logic circuit, we have low voltage. On the power circuit, we have high voltage. Certain DCRO modules specify whether the module is designed for interfacing with current source or current sink devices. Okay, so that's very important hardware-wise when we want to assemble our system. If the module is current sourcing module, then the input or output device must be a current sinking device. Okay, so here we have our sourcing input and sourcing output, and or field devices, let's say in this sensor, is sinking current. And the field device here, whatever it is, let's say it's a motor, it's also a sinking sensor because our modules are sourcing. So then or field devices or sensors should be sinking. And that also is valid when the module is sinking, devices should be sourcing. If the module is a current sinking device, then the input or output device must be a current sourcing device. So in this case, we have both input and output syncing. So the sensor and the device here, the output device here are sourcing. And we should always have matching between our modules and devices, and be careful of the type of the module and devices. Analog I/O modules. So we talk about discrete I/O module. Now we want to move on to analog I/O modules. Analog input and output devices have an infinite number of values. Okay, so it's not discrete, it's opposite of discrete. That's why we call it infinite. So it's not just 0 and 1, it could vary from a low value to the high value. Typical analog input and output vary from 0 to 20 milliamps, 4 to 2 milliamps, or 0 to 10 volts. Okay, so here we have a tank. Let's say here we have a water tank, and we have a transmitter that measures the level of the water. But the level of water cannot be 0 or 1. Yes, it could vary from, let's say, 0 to the height of the tank. And that should be translated to either amp or voltage. So if that's a voltage-based transmitter, that height should be translated from to voltage from 0 to 10. So then the output of the transmitter will be sent to the analog input module. The analog input interface module accepts analog signal and converts it to a digital signal. So anyway, you should be converted to digital signal. Why? Because the PLC accepts only digital input. The analog output module accepts a digital signal, so this is the analog output module, and converts it to an analog signal that operates the output. So it gets the digital signal from the PLC, converts that to analog output, and send it to the analog device. So here, for example, we have a level indicator. A level indicator is analog device, and then the conversion should be done from PLC to the device. The two basic types of analog input modules are voltage sensing and current sensing. A varying DC voltage in the low millivolt range, proportional to the temperature being monitored, is produced by the thermocouple. So here, in this case, we have the thermocouple and a thermometer. So thermocouple basically is a device that measures temperature, and it's a kind of thermometer. And we need to convert that analog input, which is temperature, to a digital input, and that digital input could be used by PLC. So that's why the analog modules are specific, and we must have a separate type of module for analog input and output. The main element of the analog input module is an analog to digital or AD converter. Now you could see the different type of these modules. Bipolar is the first one. Bipolar input modules can accept signals that swing between a negative and positive value. So that's why we call it bipolar, means two poles, negative and positive. Unipolar input modules can accept an input signal that varies in the positive direction only. So unipolar means one pole only. We are only in the positive numbers. And we have another definition, very important definition for analog or AD converters, analog to digital converter, which is resolution. Resolution refers to the smallest change in input signal value that can be sensed. Okay, so resolution is type of like sensitivity here. So here we have our bipolar and unipolar. On the bipolar side, you see it accepts negative and positive numbers. So minus 10 to 10 voltage. And this is just a span, yes. This is the span from 0 to 10. So the span is 10 voltage. And this one is another type from minus 5 to 5. We have also here two type of unipolar. And here you see the resolution, yes. And for both of these cases, we have 0.3 millivolt resolution. That number could be different for different type of sensors. And again, back to the definition, this is the smallest change in the input signal that could be sensed. So if the voltage changes from 0 to 0.3 millivolt, then the output basically won't get updated. Nothing happens. But when it passes at 0.3 millivolt, then the output will be updated. And the sensor now has a different output. Unlike voltage input signals, current signals are not as sensitive to noise and typically are not distance limited. So that's basically advantage. They are not sensitive to noise and they are not distance limited. So it means that basically the length of the wire does not or cannot basically lose information here. The current sensing loop power may be supplied by the sensor or the analog output module. So here we have our sensing loop. Here we have a sensor, and here we have our module. Okay, and this one is the sensor supplied power, and this one is module supply power. Okay, so here you could see the difference here where the supply power is located. Here you have the power supply located on the sensor, and here the power supply is on the module, and the module is providing the power. Shielded twisted pair cable is normally recommended for connection any type analog input signal. Okay, so here is the shielded twisted pair cable that is used. The main element of the analog output module is a digital to analog converter. The analog output module receives from the processor digital data, which are converted into proportional voltage or current to control an analog field device. Okay, so the output analog device is just doing opposite of the input device is doing, input module is doing. The analog output signal is varied under the control of the PLC program and can be used for control of an analog control valve. Okay, so this is the, let's say, our control valve, and since this is valve and the valve is not just open or shut or 0 or 1, close or open. We want to have control over the level of the valve opening. So this type of valve is an analog output field device. Here we have an example of analog I/O control system. We have our water tank and we have the analog valve, and we have a level sensor. The level sensor is also analog, so we have analog input, analog output. We have analog input and output modules on PLC. The PLC controls the amount of fluid placed in a holding tank by adjusting the percentage of the valve opening. Okay, so we want to control the level of the tank, and we want to have control on this level from our PLC. The valve is initially open 100% as the fluid level in the tank approaches the preset point. Okay, that preset point is set inside the PLC program. The processor modifies the output, which adjusts the valve to maintain a set point. Okay, so this is one example. Later we'll see how we could program it and in different languages in coming sessions.